Alrighty, so we are going to start now with Chapter 9, our first section, which is Introduction to Sequences. So today's objectives are to find the nth term of a sequence. So you would just put a number here for n, like 16th term of a sequence, which is a list of numbers. And then we're going to write some rules for sequences. So here we go. Some of the vocabulary that you're going to be introduced today here is sequence. We also have terms of sequences, which we've seen term before when we've talked about pieces of a polynomial. Infinite sequence, a finite sequence, a recursive formula, explicit formula, and then we'll also talk about iterations. So there we go. So just an introduction here to sequences. We've got our friend Fibonacci here. So he was in 1202 an Italian mathematician, Leonardo Fibonacci, and he described how fast rabbits breed. So if you ever hear about, oh man, they were like rabbits, here you go. The idea is that the couple of rabbits potentially will make an exponential amount of rabbits after quite a little amount of time. Also because their gestational period is not, like 10 months, 9 months like ours. Anyway, so Fibonacci noted that the number of pairs of rabbits each month and formed a famous pattern called the Fibonacci sequence. So here it is over here. He's saying, okay, so I have 0 rabbits, but then I take 1 rabbit and another rabbit, add them together. Now I've got 2 rabbits. 2 rabbits plus 3 rabbits. Now I've got 2 rabbits plus 1 is 3. 3 plus 2 is 5. 5 plus 3 becomes 8. 8 plus 5 becomes 13. And you can see very quickly it becomes a much larger amount of rabbits or numbers in this case. So basically what's happening is each number is growing from the previous number. So that's your first sequence here. This is also the Fibonacci sequence at work here, talking about actually how things are formed in nature. So it's an interesting spiral there. So to get on with sequences, it's an ordered set of numbers. Okay, so again, Fibonacci sequence has a certain order. Okay, so we're not going to put 55 before 34 because that's how you get to 55 is adding those two. So definitely has to have an order. Okay, and we're talking about our numbers here. The terms of each of the sequence, notice these little arrows here, is each number within the sequence. So this is the first term, it's the first number, second term, third term, so each of these are your terms. An infinite sequence is, of course, one that has this ... at the end. It's a set of numbers that continues without an end. Fibonacci sequence continues without an end. So if we were writing this in the traditional way, we'd have had a ... at the end. Sometimes sequences can also go backwards in the ... as well, so it can kind of go in both directions. It just matters if you tell them that or not. All right. Then we've got a finite sequence, which you might try to say finite or something, but it's finite. And it's a set of numbers that has a limited number of terms. So 1, 2, 3, and 4, and then we're done. A lot of times a finite sequence might have to do with something you're selling or whatever, because maybe day 1 you have 200 of the product, day 2 you have 150 of the product. So the idea is that you'd go down, but you'd have to actually end at 0. So finite sequence has an end. Alrighty. Then we have our introduction to the notation of functions, sequences. So the idea is that we have had functions in the past, okay? We've even had this as the letter y, okay? But it turns out that instead of our normal variable, okay, and this would be the independent variable right here, okay, instead of an x, we're now going to have an n. So n are like your x values or your domain. And your range is still your y values, but now instead of having an f of x, we're actually going to have an a sub n. So a is like the f and n is like the x, okay? And then let's say that you actually want to put in a number for whatever the n is. Then instead of what our traditional function notation was, which was plug in a 1, this means plug in a 1. It means the first term. Okay, so a sequence is a function with natural numbers, and so it turns out that the domain is always 1, 2, 3, and 4. Sometimes the domain can start at 0, but it usually starts at 1. So it is very rare that it's going to start at 0. So it starts at 1 always. All right. In fact, the times that it will start at 0 is in calculus, so don't plan on seeing that anytime soon. All right. So as in the domain, n, remember those were the x values previously, and the terms of the sequence as the range, which used to be our y values or f of x values, but now it's a sub n. So again, here's a nice visual of your table. Again, we used to have x's on the top, but now we have an n for term number, and then the term value or the result is going to be here on the bottom one. So that is our new notation, and this is pretty much the newest and actually the hardest to get used to. So a lot of times the easiest thing is to think that whenever you see an n, remember that it's x. Anytime that you see an a sub n, remember that it means y. Otherwise, if you're not thinking of it in your previous knowledge, then you're not going to be able to associate it. So we'll try to reference that, especially in the next section when we talk about specific formulas. So here we are with a recursive formula, and this is going to be helpful to remember, okay? So recursive formula, a lot of us will not or haven't in the past. My students haven't necessarily remembered this idea. So recursive formula is a rule in which one or more previous terms are used to generate the next term. So Fibonacci sequence very much uses the previous term to get the next term. So again, thinking back to or referencing back to that formula, if I did not know what the previous two formula numbers were or sequence numbers, I wouldn't have been able to get 55 because it was the two previous. So there's not really a way to, for instance, jump to the 30th term without knowing the 29th and the 28th term. So we can't jump. And so that's what recursive formulas are doing. You cannot jump, okay, to whatever term you want. So if we look at this notation here, again, thinking of the previous notes on what represents x and what represents y, what they're saying is the first term is 1. So a sub 1 is saying the first term. So the first term is 1. And then this here is saying second term is 1. So again, remember in Fibonacci sequence, a lot of times they actually don't start with 0, they'll start with just 1. So this is saying that the Fibonacci sequence, the first term is 1, the second term is 1, and then in order to get all of the next terms, so again, to get the next term, you're going to take the, I guess I don't know how to say this nicely, the two previous terms and add them, okay? So this here is saying two terms before. That's what minus 2 would mean. And then this part is saying one term before. A lot of times we'll actually talk about this one as the previous term. Most of the time, we will not be using n minus 2, but because we're talking about Fibonacci sequence, sometimes that's used. So generally, we will be using a sub n minus 1. That's very common. A sub n, very common. And then, of course, a sub any number is also very common. Notice here that they've also said this, where n is greater than or equal to 3. because it turns out that you cannot plug in a 1 or a 0 or a 2 in Fibonacci sequence because you have to be given the first two in order to get the third one. So this is saying a sub 1 must be given and a sub 2 must be given. And a sub 3 you can use formula for. But you cannot use the formula, this one right here, to find a sub 1 and a sub 2 because it's saying that the number of terms needs to be greater than or equal to 3 because those were given. So the third one you could use the formula. All right, anyway, so here's our notation. I've said it, of course, a bunch here, but a with a little n next to it is read a sub n. So I will be saying a sub 1, a sub 2, or the second term or the first term. But anytime that I see this, I'm definitely going to be reading it as a sub n. That's how you say it. All righty. So this next one here, we're going to find the terms of a sequence by using a recursive formula. So if we remember back to what's happening here, a recursive formula uses the previous terms. And it could be the previous term or the previous terms like the Fibonacci sequence does. So this one is not a jump. And again, if we think of a jump, we're thinking of like a linear formula that we can find the plugging in an 8, we can get that term without knowing what 7 or 6 was. So that's what we're going to do, however, in this example. And usually recursive formulas are actually easier to write because you really just need to say, what am I going to do to the previous one versus make an entire formula that will work every time. So we're going to find the first 5 terms of the sequence given this bit of information. So again, a sub 1 means that this is that the first term is negative 2. Okay, so if I think about making the sequence itself, and usually you use curly brackets in your sequence, okay, the first term is going to be negative 2, and then we would continue the sequence. This here formula is saying to get the next term, okay, and that's a sub n. You must, that's your equal sign, multiply the previous term. And remember, previous term is a sub n minus 1. That's where that's coming from. I guess I've been putting it here. By 3. Okay, so again, to get the next term, you need to multiply the previous term by 3. So that's what this part is saying. And then, of course, add 2. Okay, so they're also telling us that we're using this for term numbers that start at 2 because, again, term number 1, or I'm doing a little orange here, a sub 1 was already given. So it's just saying that you can use it for a sub 2 on. And, of course, we're only going to 5 terms. So, all right. So the next piece that we're using is this formula. And so to get the next term, I'm going to take the previous term, which is negative 2, multiply by 3, so that's negative 6, and then add 2, so negative 4. All right, and so again, do the same thing. To get the third term, I'm going to take negative 4, multiply it by 3, so negative 12, and add 2, so negative 10. And so really you're just plugging in right here the previous number. Okay, so if you think of it as kind of a function idea, to find the term, you're going to plug in 3x plus 2. But you have to do it to the previous number. So negative 10, for instance, would go in here. And so I'd multiply by 3 and get negative 30, and add 2 and get negative 28. And then our last term takes negative 28, multiplies it by 3, which is negative 84, and then add a 2, which is going to be negative 82. Move my in parentheses over there. This is a finite sequence because notice that they just wanted the first 5 terms. They wanted it to end. And then just to kind of reiterate, this is the first term, so a sub 1, a sub 2 is this guy, a sub 3 is technically that one, a sub 4, and then a sub 5, to note what each of our terms are. Alrighty. So that's the idea. And so what's going to happen on your assignment is some like this where they'll give you the formula, but then there will also be ones where you have to write the formula. So just kind of getting the idea of what do I need to do to the previous number to get to the next number. That's your recursive formula. All right. Then we have our explicit formula. And this is, it defines the nth term, or the one that you're looking for, of a sequence as a function. Okay, and so the key idea here is that you're going to be writing like a linear function. Okay, so if we think back to our linear functions of mx plus b, something like that, remember, however, that it's actually a little bit different because now instead of y, we have a sub n, and instead of x, we have an n, and then potentially, depending on what the slope is and the intercept is, those would change as well. So again, we are not going to have this format anymore. We have our n for x, and then our a sub n for our y. You're also going to end up with quadratic functions. Well, actually not quadratic. I'm thinking of exponential functions. Those are very common. And so thinking back to our exponential functions, we had something like y equals ab to the x. Okay, but again, of course, it's not going to be y anymore. It's going to be a sub n. And then, of course, this is confusing because there's an a and a b. But anyway, and then to the n. So again, we're not going to use this. We have some n's here and some a sub n's. All right. We'll also be using... those are actually pretty much the most particular ones. So that's your explicit formula. But again, any type of formula is fair game here that we have covered. So moving on to the next one, again, explicit formula. These are, again, a little bit more difficult. They're not hard, but they're just more difficult because if you're going to write it, that's where the problem comes in. A lot of times you need to take a step back and think about what you're plugging in. But of course, this one actually just gives it to you, yay, and wants you to find the first 5 terms. So really, this one you just need to plug in 1 through 5 for n. So this is going to be very natural, where you just plug in your n as a 1, a 2, 3, 4, and then a 5, and those are going to be your first 5 terms. So our sequence is going to have the first 5 terms. And remember that all of your sequences start with an n of 1. Okay, so it's not saying any certain restriction on here because it is assumed that you know that it always starts at 1. So we're going to take our formula right here and plug in a 1. If we plug in a 1, 3 to the 1 minus 1 is going to be 2. All right, so again, 3 to the 1 minus 1. Now we're going to do 3 to the 2, which is 9, minus 1, so that's 8. And again, that was just because I'm technically getting the second term, and that means n was 2. All right. Then I'm going to do 3 to the 3, which is why this is growing very fast, because that's 27. And then minus 1 is 26. Then we're going to do 3 to the 4. And 3 to the 4 is 81. And then minus 1 is 80. And we're going all the way to the 5th term. So 3 to the 5 is 243. Minus 1 is 242. And again, if you're following along with this piece, that meant that we were trying to find term 3 by plugging in an n of 3. We were trying to find term 4 by plugging in an n of 4. And then term 5 by plugging in an n of 5. So again, when writing formulas, explicit are harder, but when solving them, they're much easier, more direct. Versus when solving them, usually it's a little harder to analyze what's being said in a recursive formula, but it's a lot easier to actually write. So that is that one. This is where we're going to determine if something was linear, quadratic, or exponential. How I mentioned earlier that a lot of these equations will be one of these type. So linear patterns have a constant first difference. So if we make a table and we subtract everything, we're going to have a constant number. That's your slope, in fact. Quadratic patterns are going to have a constant second difference. So you take all of those differences you just got by subtracting and do them again. That's your second difference. Or an exponential pattern has a constant ratio. So remember, ratios are multipliers. And so we'll kind of go over an example that does that. So we're going to write a possible explicit rule for the nth term of this sequence. And there are multiple ways of going about this, but we are going to try to use this previous moment here to figure out at least if it's linear, quadratic, or exponential as we were writing it. So taking a look at this, let's see. The first thing that we're going to do is the term number. And then this is going to be the term itself. And we tend to write our tables sideways when it comes to finding out your explicit rule, just because then you can subtract and show your results a little bit easier. So the term number is 1, because remember that we're always starting at the first term. If we plug in a 2, we get 10, a 3 is 20, a 4 is 40, and a 5 is 80. Then the next piece here, our term becomes 5 at the first one, 10, 20, 40, and 80. So again, this is very clearly very much like our x's, and this is very much like our y's in a traditional function format. So now all we have to do is take our differences here and see what it takes to get from, for instance, 5 to 10. So if I take 10 minus 5, the difference is 5. 10 minus 20, 20 minus 10 is 10. 40 minus 20 is 20. And 80 minus 40 is 40. So this is what we call our first differences. And because they're not the same, that means it's not linear. Okay. So then we go ahead and take the differences of our differences. So we're going to take 5 and 10 and subtract them and get 5. 20 and 10 gets you 10. And 40 and 20 gets you 20. So again, this one is now our second difference. Remember that difference really just means subtraction. And these are not the same. And so because they're not the same, it is not quadratic. Alrighty. So pretty much we can assume that if it's not linear and not quadratic, then it's probably exponential. So how do we figure out if it's exponential? Well, now we're going to go ahead and say, how do I get from 5 to 10? what multiplier would I use? So we're not adding anymore. Now we're checking multiplying. And so if we're going to check the multiples, 5 times 2 is 10. So then we check the next one. Is 10 times 2 our next piece? And it is. And then we check the next one. Is 20 times 2 our next example? And it is. And so on. And so because of that, we now know that because it has multiples that check out, it is exponential. Because there is a constant, apparently forgot part of my sentence, there is a constant ratio. And it's 2. All right, so again, just because each of them ended up being multiplied, that means that it's exponential. So hopefully this reminds you a little bit back of Algebra 1, where we were just identifying, is this a linear function? Is it quadratic? Is it exponential? And you were just trying to figure out, is there something that adds repetitively, something that multiplies repetitively? And that's what we're looking for. So because we know that this is going to be our multiple here of 2, we can then go back to our formula of technically y equals ab to the x. Okay, but of course we're not doing ab to the x anymore, but thinking back to that, a was your first term, which lo and behold we have right here, and b was your multiplier. So as long as we take the time to replace our y and our x with the new pieces of information, which was an n instead of an x and an a sub n instead of a y, it should work out. However, I said should because if we only do an n, that means that it starts at 0. And so because this formula starts at 0, we are not going to be able to put in a 1 and get a 5 right away, because this formula or this pattern here is saying plug in a 1, get a 5, plug in a 2, get a 10. But if I rewrite this formula so that I put in the pieces that I have, I'm going to say that it's, here, we'll write it up here, a sub n equals the first term, which is 5, times our multiplier, which was 2, and to the n. But let's plug in a 1. If I plug in a 1 right here, I'm going to get 2 to the 1, which is 2, times 5, which is 10. Okay, so we end up jumping to the second term. What if I plug in a 2? If I plug in a 2, I'm going to get 4 times 5. And 4 times 5 is 20, not 10. So what happens is you actually need to put in minus 1. Because that is going to take everything that we just did, which seemed to be shifted over 1, and shift it back 1. So again, this is very key because initially our function starts at 0, but we want it to start at 1. That's a bad arrow. All right. So this ends up being our result, again, using very much similar things that we have talked about in previous lessons, but now we're talking about, of course, it's starting at 1 and not at 0. So we want to make sure that we use this formula instead. So that's the only big jump here between functions and then sequences, is that you got to be very careful when you make a formula that you double check it, that it's not accidentally starting at 0, because that's very much pushed in the function sense, because you want your y-intercepts and all of that. All right. So the next one is going to be an explicit rule for the nth term. And so again, this is not recursive. This is explicit. So this one kind of takes a little extra effort, but it's going to be the same idea. We're trying to find out, is this going to be a first difference, so then it's linear, a second difference, so then it's quadratic, or is it going to be a multiple, so it's exponential? So taking a look at the table again, remember that we had our term number, and then we also had our term. And then technically these are feeling like our x's, and these kind of feel like the y's. And the x's again start at 1 because of the first term. We don't have a 0th term. And then we have 5 options. The first term is 1.5, then it jumps to 4, then 6.5, then 9, and then 11.5. So in that case, we're just trying to find out how it moves here. So between 1.5 and 4, it turns out that you add 2.5. So 2.5 is that first difference. From 4 to 6.5, it's also 2.5. From 6.5 to 9, it's another 2.5, and then lo and behold, 2.5. So again, because all of these numbers are the same, which are the first differences, that means that it is linear. All right. And so again, we are going to use the form of a linear equation like we've used before, which would have been y equals mx plus b. However, again, we are going to rewrite the y as an a sub n and the x as a n. All right. And so then we look down at our formula and we say, okay, well, remember that the thing that changed each time is our slope. Okay, so m is the slope, which in this case is the thing that's added each time, so 2.5. This is our y-intercept. But remember that we don't actually have a y-intercept because that would have meant that the x equals 0. So we actually have to make an x equals 0. So we need to skip over and make a 0th term. So if we think of this as a pattern, to get backwards, right, from 9 to 6.5, we subtracted 2.5, subtracted 2.5. So if we subtract 2.5 again, we can get backwards to our 0th term, or our y-intercept, which is what the formula we know uses. So 1.5 minus 2.5 is -1. And so that means that our b value is actually -1. Alrighty. So let's go ahead and rewrite this so that we can check to see if it worked out. So again, we have a sub n instead of y. We have a slope of 2.5. And then instead of x, we have an n. And then instead of b, we're plugging in our -1. So now all we have to do is check to see if this works each time. So if I plug in a 1 right here, I'm going to do 1 times 2.5. Yep, that's 1. And then subtract 1, that's 1.5. If I plug in a 2, 2 times 2.5 is 5. And then subtracting a 1 is a 4. So it turns out it works each time. And so that is going to be our formula, our explicit formula. again, it's explicit because I could just plug in a 5 and get exactly to 11.5 and not have to have reference to the fourth one because it doesn't say in the formula to do something with the previous term. So that's going to be our explicit rule. Generally, what you're going to be doing in the homework assignment is talking about writing recursive rules for the previous term. So again, very helpful in the homework. To think of a sub n minus 1 as the previous term value and a sub n as the next term value. As long as you do that, it's going to be very helpful in your recursive formulas. To write a rule. A rule is just another word for a function. All right. So that should be what you need for the 9-1 assignment. And it will feel a little bit separated. It'll feel kind of like you were jumping into a new section very quickly. And that is because this is just an introduction. And so it ends up covering all of the pieces before we have each of the rules. So again, thinking in your homework in terms of these two values, meaning previous and next, that will help you very much when it comes to writing rule. All right. So hopefully that works out for you and you can try the assignment.